vendor's words, sticky or non-sticky ECMP. So on a router, we don't have layer 7 inspection. We don't maintain a state table, which is one of the things that makes it so scalable. But what this means is that we're not in a position to be able to track where every connection is going at all times. So what we do to solve this is that we build a hash table that includes layer 3 and 4 information generally, and we say that X portion of that hash will go to each server. Now, in older routers, and also in routers that don't have consistent ECMP turned on, we end up in a position where every time you add or remove a server from the pool, it regenerates this hash table, which means that now you're going to move every TCP session to a new server. And of course, if we relocate a TCP session to a new server, we're going to end up resetting that TCP session. So while a client can probably accept one TCP reset every few hours or even every few days, having rolling TCP resets every 30 seconds or so, as we say restart a fleet of servers, is unacceptable. So just to go through this, if we assume we have 3 hosts here, we have and 3 users hitting it. If we have non-consistent ECMP and this host breaks, then the TCP sessions will be rearranged. And you can see that the users that were not on the impacted server are still moving between hosts. Whereas with consistent ECMP, we only move the impacted session and then leave the other 2 sessions in a position where they were not interrupted. So the other challenge with doing ECMP is that the ICMP2 large message is not hashed correctly on any vendor's router. So the ICMP2 large message is returned when we try and send a packet to a router, outer router interface that cannot support that MTU. When the ICMP2 large message is sent back, it actually carries the layer 4 header from the original packet. So we have all the information we would need to do to correctly hash this, but none of the router vendors we've worked with are actually using this correctly. Instead, they're looking at the layer 3 information and the fact that it is protocol ICMP and nothing else. So we've had to work around this limitation. So the next thing that load balancers do is they map traffic to hosts that are not necessarily directly connected. And much like we were actually using in a layer 7 load balancer world, we're continuing to use GRE tunnels for inbound traffic. And a direct server return-like behavior is what we wanted to achieve. So we're actually only placing the inbound traffic from the internet to the server into GRE tunnels. Outbound traffic is still routed via the normal routing path we would see out of the data centers. Next, we have to advertise routes to the network to inform the network that we actually have a route, a path to this VIP at this POP. Now, we're actually doing this from the server itself, and the reason for this largely gets into the health checks that we wanted to do. For so long, we've been health checking from the load balancer onto the server. And what this means is we have some visibility of if the application is working, but we don't have visibility on if the server is about to die, or if something else is happening, or if the server doesn't have reachability to its origin servers in another data center. So we've actually been running ExaBGP, which is a really extensible package that you can use to stand up BGP from your host. And the key difference here is that while with Bird or Quagga, you're essentially running a router on your server, ExaBGP is framed in a manner that it carries out BGP commands. So you might, on Bird, say, I'm going to configure a loopback, whereas on ExaBGP, instead you're going to say, I would like you to establish this session with this neighbor. I would like you to send this route with these attributes. And ExaBGP isn't necessarily going to follow standard routing rules of, I must have this as a loopback or a static route. And you're not configuring in that manner, which from our perspective made it really easy to implement a bunch of health checks to start saying, well, we're going to run up this process. We're going to start looking at all of these attributes on the servers, heat, disk health, RAM utilization, access to origin VIPs that I need to actually be able to serve the service properly. And then if all of those pass, we'll advertise these routes. So we were able to be much more effective in pre-detecting when a server is going to fail and removing it from the rotation. The one other thing we had to deal with was a way to fast fail when a host failed. So whether it be the network cable's been knocked out or the host has just crashed, we needed to be able to tell the router in a timely manner because we're now relying on the host to inform the router. So we're running BFD inside the GRE tunnels, and the reason we selected BFD rather than GRE Keep Alives is that multiple vendors we worked with advised us that GRE Keep Alives wasn't anywhere